Okay, on the agenda today, coordinate transformations. We understand how to describe either the molecular or macromolecular nonlinear optical properties at a single molecule level. The question then becomes, how do we look at this from the level of an ensemble of many? And that will be in the local reference frame. And for microscopy, that local reference frame might be a fiber axis, it might be the surface of a membrane, or a particular direction in a crystal. And for surface analysis, that local reference frame is the surface reference frame. So how do we get from the molecule to the surface? And not surprisingly, coordinate transformations play a huge role. Just to describe the overall pipeline, we have the molecule described now. The goal is to describe the ensemble of molecules in the local frame, and then how that relates back to the Jones or laboratory frame tensor, which connects us back to the actual polarization-dependent observables. So that's the roadmap for the next couple of topics. So how do we describe an ensemble of many molecules in a local reference frame? Well, the simplest way to do it is just to coherently sum up all the individual contributions of a bunch of isolated non-interacting molecules, and that's illustrated by this summation right here. And for surfaces, we end up with an expression that looks like this one. For bulk measurements, it's a little bit different. Really, the only thing that's significantly different is the scaling by the dielectric permittivity. The reason that's in there is that the units work out nicely if you include it in this expression, if we have a bulk number density in terms of molecules per centimeter cubed. For molecules per centimeter squared, as in the surface science, it doesn't work out quite as nicely with respect to units. I'm just going to be fast and loose with units and not really worry about the fact that the units don't really work because we're always going to be dealing with relative values of the local tensor elements. So if there's a proportionality constant that we're neglecting, I may drop the epsilon naught in this one every once in a while as well. So don't be too upset if that happens, because at the end of the day, we really care about the relative values rather than the absolute values. Okay, so we've done rotation matrices before when talking about macromolecular tensors at the single molecule level, where we had to sum up a bunch of contributions of individual oscillators. It's basically the same idea for describing the ensemble for the local reference frame. We have some individual, and if we think about rotation of a vector, it's fairly straightforward. We have some vector, we put it through a rotation matrix, and this rotation matrix is the one for external rotation. I'll say more about that in a minute. And then we get the reference, the vector in the new reference frame, the XYZ reference frame, whereas we started out in the X prime, Y prime, Z prime reference frame. And there's unfortunately, several different conventions for doing coordinate system rotation, depending on how you're approaching a problem and what area of physics or chemistry you're working. We will be doing everything using a ZYZ extrinsic rotation, which is given by this set of operations for describing the rotation. And that if you look at this particular diagram and ask if you were to project the molecular X prime, Y prime, Z prime tensor or coordinates onto the laboratory capital XYZ frame, what would the projections be? And that you can get from that is described by the extrinsic ZYZ rotation that we will be using. And unless we say something else, we'll always be doing that. So that's rotation of a vector. What about rotation of a matrix? In this case, the standard classical way to rotate a matrix is to introduce two rotation operations in this sort of sandwich scheme, where we have our initial reference frame. This might be XYZ, X prime, Y prime, Z prime, the matrix described in that reference frame, and then we do, for example, two intrinsic or two extrinsic rotations, depending on how you want to look at them, and that yields the matrix in the rotated reference frame phi. Now that works fantastically for matrices. The trouble is it's hard to generalize to tensors because it's not trivial to know what to do with this on the right side. How do you take some set of 27 numbers in a 3x3x3 and then apply these input rotation operations to understand what the thing is doing? It works, the math is legit, but it's just not trivial to sort of keep track in terms of the bookkeeping. So what we're going to do is consider an alternative architecture for doing coordinate rotation that is a little bit easier to translate over to tensors of arbitrary order. And that is one where we can do the equivalent operation of this rotation of a matrix by vectorizing the matrix. So for example, if we have this 2x2 matrix right here, and we want to end up with this 2x2 matrix right here, we can vectorize it where this is the vectorized form of the first matrix, and if we take this vectorized form and multiply it by extrinsic twice, so there's not a plus phi and a negative phi. These are not inverse operations of the rotation rotation matrix. They are identical, and we multiply them by the vectorized form of the initial matrix. That gives us the rotated matrix also in vectorized form. So it's kind of it's kind of a pain because you now have a 4x4 matrix here instead of a 2x2. So I don't understand why the sandwich matrix approach is preferable when dealing with 2x2 and n by n matrices. However, as soon as we get into tensors, it really arguably is much simpler to be able to map how each one of these tensor elements transforms over into the rotated tensor through this vectorized operation, because it's pretty straightforward to calculate this Kronecker product, this outside Kronecker product of three different rotation matrices, and then map them one-to-one on the initial reference frame to the final reference frame.